Dr. Robert Chen had 15 years at NASA's Jet Propulsion Laboratory, 3 successful Mars rover missions, and a PhD from MIT, when the agency hired Paulo Mercathar, Filipino mechanical engineer from the University of the Philippines, who'd spent years maintaining equipment in remote Philippine mining operations as a mission support technician. Robert's expectations were modest at best. He'll be fine for routine maintenance, Robert told his team lead, but for critical mission systems, let's be realistic about his training background. 3 days into the mission, disaster struck. A micrometeorite impact damaged the lunar lander's thermal control system, specifically a coolant pump that regulated temperature for critical electronics. Without it, the electronics would overheat during lunar day, when surface temperatures reached 260 degrees Fahrenheit. The lander would be inoperable, the mission would fail, and the astronauts would be stranded in lunar orbit, unable to land. Mission control erupted into controlled chaos. Robert's team ran diagnostics, consulted manufacturers, pulled up technical specifications. The pump was custom designed, no spare existed on the spacecraft, and the damage was catastrophic: a cracked housing that leaked coolant. Every protocol they checked said the same thing: unrepairable in space. Mission abort. We need to abort, Robert told the flight director. The pump is beyond repair. Without thermal control, they can't land. We bring them home. The flight director grimaced. That's $8 billion and 50 years of planning down the drain. Are we absolutely certain there's no fix? Robert pulled up the schematics on the main screen. The housing is cracked here. It's a precision-machined titanium alloy component. You can't just patch it. Even if you could seal the crack, the pressure and thermal cycling would break any repair. It's impossible to fix with what they have on board. The flight director made the call. Paulo, you have 2 hours to develop a repair procedure. Chen, you verify if it's feasible. If we're going to try this, I need consensus it won't make things worse. For the next 2 hours, Paulo worked with intensity Robert had never seen, pulling up specifications, calculating thermal expansion coefficients, designing a repair procedure that used only materials available on the spacecraft. Robert challenged every step, playing devil's advocate, trying to find fatal flaws, but Paulo's logic was sound. His calculations, though arrived at through unconventional thinking, checked out. His procedure, while improvised, addressed every failure mode Robert could identify. This might actually work, Robert admitted finally. It's not how NASA would design a repair, but the engineering is solid, if they can execute it precisely. The flight director gave the go-ahead. Artemis crew, mission control. We're going to attempt a repair on the thermal pump. It's an improvised procedure, so listen carefully. For the next 4 hours, astronaut commander Lisa Martinez followed Paulo's instructions with surgical precision. Using a Dremel tool, she ground down a titanium bolt to create metal powder. She mixed it with 2-part epoxy from the repair kit, creating a metal-reinforced compound. She cleaned the crack meticulously, applied the compound, then wrapped the repair in layers of thermal tape to provide compression and heat protection as it cured. Mission control watched in tense silence as they waited for the epoxy to set in the temperature-controlled environment of the spacecraft. Then came the moment of truth. Mission control, we're pressurizing the system. Starting at 10%. Paulo's hands were clenched. Robert held his breath. 20%. Holding pressure. 30%. Still holding. The entire room was frozen. Watching telemetry data. 50%, 70, 90, full pressure, mission control, we have 0 leakage. The pump is holding. The control room erupted in cheers. But the real test came 12 hours later, when the lander separated from the command module and began its descent to the lunar surface. As they entered lunar day and temperatures soared, the repaired pump would face its ultimate challenge. Lander temperatures rising, Commander Martinez reported. Electronics at nominal operating temp. Thermal system functioning normally. The improvised repair, created with materials and techniques Paulo had learned fixing mining equipment in the Philippines, was working perfectly under conditions Robert had said were impossible. The lander touched down on the lunar surface flawlessly. The mission continued. Experiments were conducted, samples collected, history made, and through it all, the impossible repair held. When the crew returned to Earth 3 weeks later, the damaged pump became one of the most studied components in NASA history. Engineers marveled at the repair. The metal-reinforced epoxy had bonded at a molecular level, creating a joint nearly as strong as the original component. The thermal tape compression had prevented crack propagation. The procedure Paolo developed became a case study in improvised space repairs. Robert found Paolo after the successful splashdown. "Paolo, I owe you an apology. I dismissed your suggestions because they didn't fit NASA protocols. I called your solution impossible because it wasn't how we were trained to think. But you saved an $8 billion mission with improvised techniques you learned maintaining equipment in Philippine mines. That's not luck. That's engineering excellence I was too arrogant to recognize." Paolo smiled. "Dr. Chen, your training is excellent. Your engineering is world-class. But in Philippines, we learn different skills because we have different constraints. When you can't replace components, when you don't have perfect materials, when the manual says impossible, you learn to improvise, not randomly, but using engineering principles applied creatively. My grandfather repaired Jeepney engines with whatever he could find. My father kept mining equipment running in remote sites with no spare parts. They taught me that impossible usually means we haven't figured out how yet." The story spread beyond NASA. The Filipino technician who'd saved the lunar mission with improvised repairs became a symbol of resourceful engineering. Universities began studying constraint-based innovation, how limitations force creative problem-solving that sometimes exceeds conventional solutions. Paolo was promoted to mission systems engineer and became an instructor, teaching NASA personnel about adaptive repair techniques. His course, Improvised Solutions for Critical Systems, became mandatory for all mission support staff. He taught them to think like Filipino mechanics and engineers who'd spent careers making impossible repairs because failure wasn't an option and replacement parts weren't available. Robert became Paolo's strongest advocate and co-instructor. "I spent 15 years at NASA believing that proper engineering meant following established protocols with perfect materials," he'd tell classes. Then a space mission was about to fail, and a Filipino engineer used techniques learned from his grandfather's jeepney repairs to save it. He didn't violate engineering principles, he applied them more creatively than I'd been trained to think. The best engineering isn't perfect materials and unlimited resources, it's solving problems with whatever you have using fundamental principles applied brilliantly. 5 years later, when a critical system failed on the International Space Station, astronauts used Paolo's improvised repair methodology to fix it, combining techniques from his lunar pump repair with new adaptations. The repair worked, and back on Earth, a new generation of NASA engineers learned that sometimes the most advanced engineering doesn't come from labs with unlimited budgets. It comes from Filipino mechanics who learned to keep jeepneys running, mining engineers who improvised repairs in remote mountains, and technicians who understood that impossible is just a challenge waiting for someone with the right combination of knowledge, creativity, and the Filipino spirit of Bahala na. We'll find a way, because we must.